तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We had introduced ourselves to the concept of Laplace transformation of a function of time in the last class, and we had a look at the Laplace transforms of some important functions of time like the unit impulse function, the unit step function, and the two sinusoidal functions cos omega naught t and sin omega naught t. Let us first recapitulate some of the important points that were discussed in the last class. We are concerned with functions of time which are causal. So the f of t which we are concerned with are causal, that is f of t is 0 for t less than 0, and further we said they are of exponential order. That means limit as t goes to infinity of f of t e to the power of minus st goes to 0 for real part of s greater than some number sigma c for some sigma c which is a function of f of t. So if the function of time is of an exponential order, that is as t goes to infinity, this e to the power of minus st is able to pull this down to negligible proportions, then for such some time functions we said we have a Laplace transformation f of s which is given by the integral from 0 minus to infinity of f of t e to the power of minus st dt, that is the forward Laplace transformation formula, and the inverse Laplace transform is given by 1 over f t is 1 over 2 pi j c minus j infinity to c plus j infinity of f of s e to the power of st ds. This is the inverse Laplace transformation formula, and this contour of integration which extends from c minus j infinity to c plus j infinity is a vertical line in the region of convergence of the Laplace transformation. That means c must be larger than sigma c, and this contour of integration, as I mentioned, is referred to as the Bromwich contour. Now as a result of this, the Laplace transformation that we get is usually a rational function for the type of functions of time that we consider. So for the given f of t that we are having, we have an f of s which is a rational function, and this rational function, by rational function we mean the ratio of two polynomials in S, and this could be, the two polynomials could be put in the form m if the numerator is factorized as s minus z1 s minus z2 down the line to s minus zm, and the denominator likewise is factorized as s minus p1, s minus p2, s minus pn. Then the Laplace transformation f of s is defined by the values of the z values, z1, z2, z3, zm, and the values p1 to up to pn, apart from the constant multiplying factor m. So this f of s can be represented in the complex plane by the location of the zeros of f of s and the poles of f of s. So zeros are normally marked by means of small circles. So these may be zero locations. Poles are marked by a crosses. So there may be a pole here, a pair of poles here, etc. So the pole and zero locations are marked in the S plane. So the pole and zero locations of f of s completely define f of s except for the multiplying factor m. And we also note that as long as the coefficients in the two polynomials are real, then any complex pole is accompanied by its conjugate, any complex zero is accompanied by its conjugate. And the abscissa of convergence is sigma c, the abscissa of convergence is larger than the maximum value of the real part of pi. So whatever the pi you are having is the maximum value of the real part of pi I from 1 to n. So that will be define the abscissa of convergence. That means the region of convergence starts from the rightmost pole. So if this is the rightmost pole, anything beyond that is the region of convergence. So the maximum value of the real part of the poles defines the region of convergence. And we have seen this in the case of simple functions like the unit step function, which has where sigma c is 0, the e to the power of minus 2t where sigma c is minus 2, and so on and so forth. That is what we have seen earlier. A few comments about the notation. As I mentioned, the Laplace transform exists for unilateral Laplace transform that we are talking about, exists only for causal time functions. So if f of t by definition has a value for negative values of time as well, to make sure that we are talking about the truncated part of that function of t, we normally write f of t ut, to make sure that f of t, the composite function, is 0 for negative values of time. Often instead of f of t ut, we use simply f of t when there is no cause for confusion, when there is no room for confusion. In other words, example, suppose e to the power of minus 2t, this is f of t, but we can't find the Laplace transform of such a function. We have to find the Laplace transform of e to the power of minus 2t times ut. So when you have got 1 over s plus 2, the inverse Laplace transform of that is e to the power of minus dt ut. Instead of that, we write e to the power of minus 2t itself, with the understanding that we are talking about e to the power of minus 2t valid for t greater than or equal to 0. So as long as we have understanding that whatever time function we are having is valid only for t greater than or equal to 0, and it is 0 for negative values of time, instead of e to the power of minus tt ut, we often write e to the power of minus 2t to save our writing. Another point is, suppose we have a constant Laplace transform of some constant k. Again, by definition, a constant k exists for all time values of time, but in the context of Laplace transform, we assume that this function is a value k starting from t equals 0 minus, because we can treat only functions which are 0 for negative values of time in the Laplace transformation consideration. Therefore, even if you want to
find the Laplace transform of a constant, we regard that constant, that we have that function to have a value k starting from t equals 0 minus and 0 for values of t less than this. So when we are talking about a Laplace transform of a constant, we treat this as Laplace transform of k ut and say this is k upon s. So we do not sometimes exhibit specifically this u of t, which is understood, just to say or write it. Another feature of the common notation is, you recall that I said cos omega naught t ut has Laplace transformation s over s squared plus omega naught squared. We have taken a particular angular frequency omega naught and truncated it at t equals for negative values of time and arrived at this Laplace transformation. Now s is equal to sigma plus j omega. The imaginary part of s is also given the symbol omega. It is a running variable, and to distinguish that running variable omega with this omega, so we have given a special symbol omega naught. But in our manipulation we very rarely decompose s as sigma plus j omega and look at the imaginary part of s. So where there is no confusion, we even write simply cos omega t having a Laplace transform as s squared plus omega squared. Often this is written in this manner. In this notation we understand that this omega is not to be confused with the imaginary part of this s. This is omega is a particular value of omega associated with the trigonometric function. This should not be confused with the imaginary component of s. And secondly, as we mentioned earlier, actually we are talking about cos omega t ut, but this additional function u of t is often dropped, assuming that we are talking about functions which has this functional notation only for t equals 0 plus onwards, 0 minus onwards. So often instead of writing like this, we simply say cos omega t as the Laplace transform s over s squared plus omega squared. These are minor deviations in the notation we often find to simplify the writing out the various expressions. This type of simplification is resorted to. But basically we must note that whatever function we are talking about is assumed to be 0 for values of t less than 0 minus. Let us now take a look at some of the important properties of the Laplace transforms. We use the notation that f of t has the Laplace transform f of s, and f of t is the inverse Laplace transform of f of s, capital F of s. Most of the properties that we are going to discuss parallel those which we had already discussed in the context of the Fourier transform. So as we go along, you compare the properties that we are discussing here with those that we had discussed earlier in the context of Fourier transform. They more or less are similar, except for minor variations which arise as a result of the fact that the Laplace transform concerns itself essentially with causal time functions, whereas the Fourier transform deals with functions which can exist from t equals minus infinity to t equals plus infinity. So basically that is the difference, and that creates some differences. Otherwise the properties are quite similar. First property is something which we already assumed, is the linearity property. What we mean is, if f1 of t has the Laplace transform f1 of s, if f1 of t has the Laplace transform f1 s, and f2t has the Laplace transform capital F2 of s, then a combination of C1 F1 of t and C2 F2 of t, where C1 and C2 are arbitrary constants, a linear combination of these two, is having Laplace transform C1 of F1 of s plus C2 of F2 of s. There is nothing much to prove about this. You plug this find out the Laplace transform of this. You plug this into the expression for the Laplace transform defining integral, break it up into two parts, and you can easily show it. There is no difficulty in doing this. As a matter of fact, we have assumed this relationship. If you recall, when we are trying to find out the Laplace transform of cos omega naught t, we said cos omega naught t is 1/2 of e to the power of j omega naught t plus e to the power of minus j omega naught t, and therefore there we have already made use of this linearity property. So we need not discuss this any further. This is quite obvious and it can be readily demonstrated. The second property we are going to talk about is differentiation in time domain. We ask the question, what is the Laplace transform of df by dt? This is the question which we would like to answer. Given that f of t has a Laplace transform capital F of s, we would like to find out what is the Laplace transform of df by dt, assuming that the Laplace transform of this differentiated function exists. Then we set up the differential equation, just defining integral 0 minus to infinity of df by dt e to the power of minus st dt would be the Laplace transform of this derivative of this function of time. Now this can be integrated by parts, You take the integral of df by dt, which is f of t e to the power of minus st, evaluated between the limits 0 minus to infinity, minus integral from 0 to infinity of f of t, and take the derivative of e to the power of minus st with reference to time. So minus s e to the power of minus st dt. So when you substitute these two limits in the first expression, in the region of convergence as t goes to infinity, limit as t goes to infinity of f of t e to the power of minus st, that goes to 0. That is the definition of the value of s that we are going to take in the region of convergence. So at the upper limit this is 0, at the lower limit e to the power of minus st becomes 1, and therefore you have got f of 0 minus because it is the lower limit, minus of f of 0 minus. And here the integration is with reference to s, therefore s times 0 minus to infinity of f of t e to the power of minus st dt. This integral yields capital F of s, the Laplace transform of f of t itself. Therefore this is s times f of s. So this you have s times f of s minus f0 minus. That is the Laplace transform of f prime t, which is the derivative of f of t. This is assuming that f of t that we are talking about, we want to take the behavior of f of t for t greater than or equal to 0 minus. That means when we are taking the derivative of the function of time, we take into account the variation of f of t from 0 minus onwards. Often we would like to find out the Laplace transform of f prime t for t greater than or equal to 0 plus. That means any jump that this function has got in transiting from 0 minus to 0 plus, we would like to exclude. That the derivative we want to take only from 0 plus onwards, we would like to disregard whatever is happening before that. In such case, this will be the Laplace transform of that will be sfs minus f0 plus. That means we are now talking about the Laplace transformation of the derivative starting from 0 plus instead of 0 minus. The meanings of this will become clear as we take an example. So in the literature you find that Laplace transform of f prime t is written either in this manner or in this manner. Both are equal. both are correct, depends upon whether you want to consider the derivative starting from 0 minus or 0 plus. Let me illustrate what we mean by this by an example. Let us take f of t to be a unit step function ut. So you have, this is f of t. Now let me say that I want to find out the derivative f prime t for t greater than or equal to 0 minus. So I would like to take the derivative of this function starting from 0 minus. So as you take into account the variation of f of t starting from 0 minus, from 0 minus to 0 plus it goes through a jump of 1, 0 minus to 0 plus. So the derivative of this function at t equals 0 is an impulse, because it is jumping from 0 to 1. So derivative is infinite, and when you integrate with the impulse you get a step of 1. Therefore the derivative describing the behavior of this function from 0 minus to 0 plus is an impulse. And from t equals 0 plus onwards there is no derivative, it is 0 because it is a flat function of time, therefore this is 0. So f prime of t greater than, taking into account our the variation from t equals 0 minus, is a delta function delta t. On the other hand, if you want to consider the derivative only starting from t equals 0 plus onwards, from 0 plus onwards the variation of this function, there is no variation, therefore it is 0, and from all negative values of time we assume the function to have 0 value, therefore f prime t is identically 0. So for this, that is the function. Now let us see the Laplace transform of this, we know is 1 over s. The Laplace transform of the unit step function is 1 over s. What is the Laplace transform of this? If you ask this question, f prime of t greater than or equal to 0 minus, you must use this formula, s f of s. You must use this formula, s f of s minus f 0 minus. This is the formula that we have to be used. We want to take the derivative starting from t equals 0 minus. Therefore you write s times 1 over s minus, what is the 0 minus value of this f of t? It is 0. Therefore this is equal to 1, and we know that the Laplace transform of a unit impulse function, which is the derivative of this, is equal to 1. On the other hand, if you want to consider the derivative to be 1 which has a value from t equals 0 plus onwards, then we use this formula, which is s f of s minus f 0 plus. So that will be s times the Laplace transform of f of t 1 over s minus f 0 plus. The f 0 plus of this unit step function is equal to 1. Therefore you substitute 1 here, and that will be 0, and that is as it should be, because our f prime t in this case is identically 0, its Laplace transform as well will be identically 0. So that is the distinction between these two formulas. Depending upon how you want to take the derivative, whether you want to consider the derivative from t equals 0 minus or 0 plus, so you can use either of these, and that the difference between these two will be the Laplace transform of an impulse if there is any existing at the origin. Now let us now proceed further and consider the second derivative of this. That means what is the Laplace transform of d squared f dt squared. Now the second derivative d squared f dt squared is after all the derivative of d by dt of df by dt. Since we know the Laplace transform of this, we have to apply that formula which we already derived. So this will be s times the Laplace transform of df by dt is s f of s minus f 0 minus, I will continue writing 0 minus because that is more general, minus the value of the derivative df by dt at t equals 0 minus. So I will write this f prime 0 minus. So that will be s squared f of s minus s f 0 minus
minus f prime 0 minus.
So, the Laplace transform of the second derivative of a time function in terms of the Laplace transform of the original time function is given in this manner, and this can be continued. So, a general formula for the Laplace transform of the nth derivative dn f dtn can be written as s to the power of n f of s, we are talking about the nth derivative of a time function, minus s n minus 1 f 0 minus, like that you take. Next term will be minus s n minus 2 f prime 0 minus down the line to f n minus 1th derivative evaluated at 0 minus. That is how it will be. We do not have to remember this formula. All we should know is the formula for the derivative, and then one can extrapolate this in this fashion. That will be, in fact, you can easily get this by repeating the application of the derivative formula. We have seen how differentiation in time domain carries over in the transform domain by multiplication of f of s by s and adding on to it the information regarding the initial value of the quantity which is being differentiated. Let us look at an application of this. This application is important in the sense that the result that we are going to get here will be used over and over again in circuit analysis. Let us consider an inductor of L henries carrying a current I of t. Let the voltage across the inductance be VL. So, these are the two terminals of the inductor, and you have a current IT passing through L generating a voltage VL. The fundamental rule relating VL and IT in time domain, this is VL of t of course. VLT equals L times di dt. Now, if you know the Laplace transform of the current IT, then we should be able to find out the Laplace transform of the voltage VL of t using the differentiation rule that we have just now studied. So, let us Laplace transform the left hand side and the right hand side. Assume that I of t has the Laplace transform I of s. So, if you make the Laplace transform of the left hand side and right hand side respectively, and let VL of t have the Laplace transform VL of s, then we have VL of s equals L times the Laplace transform of di upon dt will be s times I of s minus I0 minus. So, we can write this alternately as Ls times I of s minus Li0 minus. Now, 2 points to be noted here. One, time domain quantities are given lowercase letters VL and I. When we make the Laplace transform of that, we use the capital letters VL of s and I of s. This is the convention. Secondly, we are interested in finding out VL of t starting from 0 minus onwards. There is a possibility that I jumps from 0 minus to 0 plus. So, if you want to take the derivative of that current, including the transition from 0 minus to 0 plus, then we must take the initial condition here as 0 minus. On the other hand, if you are interested in the behavior of VL of t from 0 plus onwards only, and you would like to consider all values of VL from before 0 minus to be 0, then we have to take this I as 0 plus. But we are going to illustrate this taking 0 minus values because that is a more general situation, and so optionally of course, as I said, you can take 0 plus as well. So, this equation tells us that if you know the Laplace transform of current IFS, you can calculate VLFS in this manner. But to do this, you must know the initial value of the current. We can invert this expression and find out IFS in terms of VLFS as well. So if you do that, then IFS can be written as VLFS divided by LS plus, because you are going to transfer this to the other side, you get I0 minus over S. So that gives you an alternative expression relating the terminal current and terminal voltage in the Laplace transform domain. IFS is VLFS over LS plus I0 minus over S. So both these equations now are the terminal equations of an inductor in the transform domain. This is the terminal equation of an inductor in the time domain. These are the equations in transform domain. Both are equivalent to each other. Notice one thing, that the derivative operator is removed. These are purely algebraic equations. However, the extra term that you need to have here information is the initial conditions in the inductor. Now, provided the initial conditions are 0, suppose I0 minus is 0, there is a proportional relationship between VLFS and IFS. VLFS is LS times IFS. IFS is VLS over LS. That means there is a kind of generalized impedance to the current flow in the transform domain. If a current IFS passes through an inductor, the voltage is LS times IFS. So LS can be regarded as the generalized impedance of the inductor in the transform domain. Same thing here also, VLFS over LS. So 1 over LS can be thought of as the generalized admittance of the inductor. The impedance concept, the proportional relationship between a voltage and current in whatever domain you are talking about, transform domain or j omega domain in the sinusoidal circuit state situation, are all valid provided you don't have these extra terms. That means if there are no initial conditions, there is a proportional relationship between voltage and current in the transform domain. These initial conditions spoil that character, but we will see how to take care of that later on. Now, this particular equation can be represented by means of a circuit representation like this. We have an inductance. We can think of that having a generalized impedance LFS, and we have a current passing through it, not the raw current but the transformed current, the Laplace transform variable. And across the terminals of the inductor, we must have a general voltage VLFS. So this is the voltage across the terminals of the inductors. We know that VLFS is LS times IFS minus L I0 minus. So this current IS passing through LS will develop a voltage which is LS times IFS in the transform domain. But to complete the picture, we must have an additional term here, minus L I0 minus. And this quantity is independent of IFS. So L I0 minus is independent of IFS. Therefore, there must be an extra voltage here which is independent of IFS. That is equivalent to a voltage source. So you must have a voltage source in the transform domain which is L times I0 minus, like this. So this description answers this equation. That is, this circuit VLFS can be thought of as IFS passing through LFS developing a voltage LS times IFS plus minus Li0 minus, because this is a drop followed by a rise. Similarly, if you want to model this equation by means of an equivalent circuit representation, we have an element having a generalized impedance Ls with a terminal voltage VL of S. So naturally the current here will be VL of S over Ls, but the terminal current Is is larger than this by an additional value. Therefore, you should have a current source which is I0 minus over S. So the sum of these two currents will be your terminal current IFS. So this then is another equivalent representation of an inductor in the transform domain. We have an inductor having generalized impedance Ls in parallel with a current source of strength I0 minus over S in the transform domain. This is the terminal relation. So you have two equivalent circuits for an inductor which incorporates the initial value of the current also in the transform domain. Both these are called transform diagrams. Transform diagram pertaining to an inductor. One incorporates a voltage source, the other incorporates a current source. So depending upon your convenience in a circuit analysis problem, if you favor the use of a voltage source, we use this. On the other hand, if you are in love with a current source, you can use this. In particular, if you have a network in which the node equations are preferred, the preferred method of solution, maybe you would like to have a current source. But both are equivalent. The important thing to keep in mind is that if the terminals of the inductor in the actual circuits are A and B here, the terminals in the transform diagram are these A and B. We should not think that the terminals of the inductor in the transform diagram are these two, because the totality of the structure here represents the inductor carrying an initial current. So that is to be kept in mind. What we have done here is representation of an inductor in the transformed domain, where the variables in the circuit are the transformed variables, not the functions of time. This is the Laplace transform of the voltage, this is the Laplace transform of the current. So the variables are transformed variables, and the element strength is Ls. This is called the generalized impedance of an inductor in the transform domain. The generalized impedance of an inductor in the transform domain is Ls. In a similar fashion, we can give similar representations for a capacitor with an initial charge on that. That we will postpone a later time. We will not do this in great detail at this point of time. Just as we have a generalized impedance Ls for an inductor, for a capacitance it turns out that the generalized impedance is 1 over Cs. We will do that later. But our point in presenting this at this stage is to show an application of the derivative rule in the Laplace transform theory, how we can apply that to evolve circuit models of this type. These are called transform diagrams. So we have a transform diagram of a whole circuit. We have similarly generalized impedances for inductors, capacitors, and so on. The whole assembly is referred to as the transform diagram. This is the transform diagram pertaining to one element, which is an inductor. So after having considered this, we will now go on to study the third property of the Laplace transformation, multiplication by t. So we would like to ask the question, what is the Laplace transform of t of t? This is the question that we would like to ask. So the Laplace transform of t of t is 0 minus to infinity t of t e to the power of minus st t. This is what we would like to ask. Now to do this, let me take d by ds of f of s. Suppose I want to take the derivative of f of s, which is the Laplace transform of f of t. This is d by ds of 0 minus to infinity of f of t e to the power of minus st dt. This is f of s. The integration is with reference to t, and we are taking the derivative with reference to another variable. So we can introduce this inside the integration sign, and this can be written as 0 minus to infinity of f of t d by ds of e to the power of minus st dt. And this, when you take the derivative of this with reference to s, you get a minus t sign outside. So 0 minus to infinity of, I will put a minus sign because of that, t of t e to the power of minus st dt. And that is exactly what we are having here, 0 minus to infinity t of t e to the power of minus st dt, and that integral is equal to minus d by ds of f of s, as we can see. So this integral is equal to minus d by ds of f of c, because it's a negative sign. Therefore this will be minus d by ds of f of s. So when you multiply a function of time by t, as far as the transform is concerned, it is equivalent to the negative of the derivative of f of s with reference to s. So you can see that there is a nice arrangement here. You multiply by t, you get minus d by ds of this. On the other hand, when you take the derivative of f of t, df by dt, you are multiplying that by s f of s. In the derivative formula, you get d by dt of f of t has the Laplace transform s times f of s. On the other hand, when you multiply t of t, it is d by ds of f of s, except for this negative sign, it is somewhat a dual relationship exists. Now, based upon this, let me extend this result. Suppose I take t squared f of t, then t f of t is minus d by ds of f of s. Therefore, I must write minus of d by ds of the Laplace transform of t of t, which is minus d by ds of f of s. So this will be minus 1 squared d squared by ds squared. That's how it will be. So you have Tn f of t. It turns out to be, if you take Tn, you have minus 1 raised to the power of n, the nth derivative of f of s. All the time we are assuming that these are causal functions. What if I write Tn f of t, we assume that Tn f of t will be 0 for negative values. So this is understood. So let me take simple example. We know that u of t has the Laplace transform 1 over s. Now what happens if I take the Laplace transform of t ut? I multiply this by t. Then you must take the negative or the derivative of this with reference to s. Minus d by ds of 1 over s, and that is 1 over s squared. And t ut is indeed RT. So the Laplace transform of a ramp function is 1 over s squared. So we can write the extend our Laplace transform pairs, the table. We have already considered u of t, delta t, sin omega naught t, cos omega naught t. We can also say RT Laplace transform is 1 over s squared. Now suppose I take t squared ut. This is t ut, of course. T squared ut. That means you must take this derivative of this once again and attach a negative sign. So if you do that, it is minus 2 over s cubed will be derivative, and you attach a negative sign, it will be 2 over s cubed. Continuing in this fashion, suppose I have t cubed ut, then it will be, again you take the derivative of this, it will become 3 times 2 divided by s to the power of 4. And if you proceed further in this fashion, if you have Tn ut, then you have n factorial over s to the power of n plus 1. That's how it goes. As we take higher and higher powers of t, the Laplace transform goes in this manner. Okay. Let us now consider another example. Suppose I have e to the power of minus alpha t ut, then we know its Laplace transform is 1 over s plus alpha. Now suppose I multiply this by t, e to the power of t times e to the power of minus alpha t ut, then its Laplace transform is minus d by ds of 1 over s plus alpha, and that is indeed 1 over s plus alpha whole squared. 1 over s plus alpha whole squared. And suppose I have t squared e to the power of minus alpha t ut, then it can be shown that this is indeed 2 over s plus alpha to the power of 3. And in fact, as before, you have t to the power of n e to the power of minus alpha t ut. You continue in the same fashion, you have n factorial
over s plus alpha raised to the power of n plus 1.
That is how it goes. So, in other words, we need not remember the Laplace transforms for t multiplied functions like this, either e to the power of minus alpha t or in terms of u of t. It is enough if you know the basic formula for ut, then whenever it is multiplied by t to the t square, t cubed, etc., then you can easily derive them without any difficulty. Let me now take the next property, which is the integration, which is again very important and which commonly occurs. Let me consider f of t dt indefinite form, which we can always regard this as 0 minus to t of f of t dt plus, suppose this f of t is a current, let us say, then what we are doing is by integrating you get the charge. So, we often find it convenient to consider the charge at a function of point of time t as the initial charge plus the additional charge that is carried by the current in the point from 0 minus to t, in the interval 0 minus to t. So, this is the value of the integral between the definite limit 0 minus to t plus the initial value of this integral. We will write this as f inverse minus 1 within bracket 0 minus, that is, this is the initial value of this integral plus the addition to the integral in the value in the interval from 0 minus to t. So, this is how we can put the indefinite integral in the form of a definite integral plus the initial value. Now, in order to find the Laplace transform of that, let us find the Laplace transform of these two individual quantities. So, 0 minus to t of f of t dt, suppose I call this g of t, then we know straight away that g0 minus is equal to 0 because we are taking the integral between the two limits, same limits 0 minus to 0 minus, it must be 0. And further, let limit as t goes to infinity of g of t e to the power of minus st equals 0 because we are taking the value of g of t to be Laplace transformable and we are taking the value of real part of s is such that this tends to 0. That means the value of s is within the region of convergence of the Laplace transform of g of t. With these conditions, and further we also know that g prime t, the derivative of g of t, is f of t. G prime t is f of t because this is the integral of this. The fundamental rule of integration tells us that the derivative of this is going to be f of t. Using this, the Laplace transform f t dt, Laplace transform of that equals 0 to infinity of this quantity, which is gt e to the power of minus st dt, and that would be obtained as, let us do this integration by parts. I will take g of t e to the power of minus st, I take the integral of this divided by minus s between 0 minus to infinity plus 1 over s 0 minus to infinity of e to the power of minus st g prime t, the derivative of g of t times e to the power of minus st dt. And this will be at the upper limit, this will be 0 because limit as t tends to infinity of g to the power t e to the power minus st, this is 0. At the lower limit, this is also 0 because g of 0 minus is 0, therefore this is 0, and you have 1 over s of g prime t is the same as f of t, therefore 1 over s times f of s. So, we have that the Laplace transform of this is f of s over s, and this is a constant. F, the initial value of the integral is going to be a constant, that will be the Laplace transform of this is f initial value divided by s, and the Laplace transform of this is f of s over s. So, we have Laplace transform of the indefinite integral f t dt
as f of s over s plus the initial value of the integral at 0 minus over s. On the other hand, if you want to take the Laplace transform of the definite integral 0 minus to t of f of t dt, that means the initial value of the integral is ignored, then this is simply f of s over s. F of s over s. That these are the two important results relating to the integration, and we can make use of this when suppose I have a capacitor value C, and this is the voltage across the capacitor VCT and the current to the capacitor is IT, then we can write VCT is 1 over C, the integral of the current, which is the charge on the capacitor. I can write this further as 1 over C 0 minus to t of I dt plus the initial charge on the capacitor 0 minus. So, if I take the Laplace transform of the various quantities, I have Vc of s, the Laplace transform of the capacitor voltage is 1 over C, this is I of s over s plus a constant, this is a constant q0 minus over s. So, I can write this as Is over Cs plus q0 over Cs, which is Is over Cs plus q0 minus over C is the initial value of the voltage across the capacitor. Therefore, I can write this as Vc0 minus over S. So, this equation can be represented nicely in this fashion. This is the Laplace transform of the current, this is the Laplace transform of the voltage across the capacitor, and this is the generalized impedance 1 over Cs. Is passing through 1 over Cs will create this voltage drop. In addition, I have the initial value of the capacitor voltage divided by S, a voltage source. So, this is then the transform diagram of a capacitor. In the same way as we have derived it for the case of an inductor. An equivalent in the term in the parallel form in a capacitor in parallel with a current source can also be derived. I will not do that, it will leave it as an exercise for you, that it can be drawn up in a similar fashion as we did in the case of an inductor. It is very important now to see that you must distinguish between these two formulas, and when you have an initial charge on the capacitor as we have, that is equivalent to a source here, which is the represents the initial charge on the capacitor or the initial voltage across the capacitor. So, we will stop this discussion of the properties of Laplace transform at this point. So, in this lecture what we have covered is, to start we started off with a review of the definition of the Laplace transformation and the type of functions which are Laplace transformable. Then we went to discuss the various properties of the Laplace transforms. In particular, what we talked about was the linearity property. Then we talked about the derivative, how the derivative of a time function carries over in the transform domain. Then we discussed how multiplication of f of t by various powers of t, how such functions are transformed in the Laplace transform domain. In particular, we said t of t has a Laplace transform minus d by ds of f of s. Then we went to the integration of the time functions, and we distinguished between the definite integral and the indefinite integral, and in both the derivative case and the integral case we saw how they can be applied to the situation of a inductor and a capacitor, how the relation between the transformed variables of currents and voltages across inductors and capacitors can be represented by means of such diagrams, which we called transform diagrams. We will continue the discussion of the properties of Laplace transforms in the next lecture.